We're the headliners. We're on at the end of the day because obviously this is the topic everybody's been most excited and waiting to hear about. So we'll be talking about network piping distribution options. My name is Sue Doherty. I work for NY-GEO. I'm on the newly formed New Construction plus Thermal Energy Networks team. I was formerly on the Community Thermal Networks team. We've reorganized a bit in the past couple weeks, but I'm still focused on managing the large-scale thermal program and the activities related to large-scale thermal and thermal energy networks. So I'll just do a brief overview of the funding opportunity we have available for large-scale thermal systems, and then I'll turn the presentation over to the panelists. First, Mike from Ramble is going to talk about different piping configurations and the considerations for selecting different piping configurations. Brian from Salas O'Brien, who apparently didn't leave the stage, so we're just going to keep him around for the next one. He's going to give some project examples and why one piping configuration might be suitable for a particular project site, and go through a few different examples. And then Steve is also going to share important information for project sites that currently have steam distribution piping and how they can transition off of steam distribution piping to lower temperature distribution networks. And I should have had this slide up when I was sharing all that. So I'll talk about what large-scale thermal is in the context of the funding opportunity we currently have at NY-GEO to support large-scale thermal. In very simple terms, large-scale thermal is a system that provides heating, cooling, and hot water to either a single building or multiple buildings using heat pumps and low-carbon thermal resources. Some examples are provided on this slide here. Geothermal is obviously one of those, but other thermal resources that are often explored or used in large-scale thermal systems are waste heat, surface water, which could be lake, pond, running water like a river, wastewater, air source heat pumps are part of that mix, and then thermal storage can also be integrated in there to improve efficiency, be used for load shifting. And for large-scale thermal, if you remember, we used to run a program called the Community Heat Pump Systems Program, which preceded the large-scale thermal program, and that was focused on exploring opportunities for thermal energy networks in New York State. The large-scale thermal program is a little bit more expansive than that, so it's not focused exclusively on network systems. It's funding support for both large single building designs as well as multiple buildings, and it may be a network system. So a network system is part of the bigger mix of solutions that can be used to address heating, cooling, and hot water for a site. And keeping with the theme of large, we set minimum thresholds for both single building and multiple building projects. So to be eligible for funding through the program, large would be for a single building at least 100,000 square feet of conditioned space. For a multiple building project, either networked or non-networked, it must be at least 250,000 square feet of conditioned space. This slide gets into the details of the funding that's available through the program. So this program is focused on design projects. It's meant to take a project that's already found a technically and economically feasible solution, move that through the design phase, and become prepared for construction. So we're trying to support projects to make them shovel-ready. And there's different funding levels for projects that are existing building or new construction. So existing building projects can get up to $750,000 award, and a new construction project can get up to $300,000 award. There is a 50% minimum cost share from the proposing team. And like I said, this supports both single and multiple building projects, and that could be either networked or non-networked approach. And for projects that may not quite be at the design phase, we still have funding support available through our FlexTech program, which is PON 4192. And that can be used for site planning, and that site planning could be a campus, college campus, medical facility, a community. This program will allow you to explore the range of different options for decarbonizing either a single building or group of buildings. And this is a rolling solicitation, so you can apply at any time to request 50% cost share to perform a feasibility study. If you have questions about that, you can access one of the links that will be provided in the slides, or reach out to me, and I'd be happy to connect you with our team over within the FlexTech program to help get you started with a study. And for projects that have moved through the feasibility phase already, they've come up with a solution that they believe is technically and economically feasible, and they meet all of the other program criteria for the large-scale thermal program. We do have a funding round that's open right now. There's a due date of July 31st, so you can scan that QR code. That'll take you to our program website, which will then direct you to the solicitation page. But within the program website, you can find a list of the existing projects that we have supported through our community heat pump systems program, and that'll give you a sense of the types of project opportunities we've funded in the past, as well as many feasibility studies that we have funded, and what's currently being explored within New York State for thermal energy networks and large-scale thermal projects. And if you would like to get in touch with me, you can reach me through the email address that's provided at the bottom of this page. And just to set the stage a bit for the panelists who will get into more details about different piping configurations for thermal energy network systems. Thermal energy networks are not a new technology. They're just one possible solution for heating and cooling buildings and providing domestic hot water. And earlier generation systems often use steam or high temperature hot water, and over time, to improve efficiency, these systems have gradually become more efficient by decreasing the distribution temperatures of these networks. And oftentimes there are two buckets that these thermal energy networks will fall into. One is a centralized solution where you're producing the heated and chilled water in a central plant and then distributing that to buildings. There's also a solution that's being explored often called an ambient temperature loop system. So you have a lower temperature network that's distributed to multiple buildings, and then buildings have heat pumps that are then used to produce hot and chilled water. And even within those two general categories, there are many different permutations and options and considerations when selecting a network to optimize the performance, both the economic and technical performance. And that's why my panelists are here, because they'll be discussing those considerations and the process used to make that, that decision framework for how to select the right piping configuration. And as I was watching all the very talented early career people speak throughout the day, I kind of started to sink into despair as I realized that this is a 30-year-old reference to a television show, and that many folks in the audience would not even get it. But this question is intended to be answered by the panelists here, who are going to go through what is the difference between all these different piping networks, and how do we arrive at the right solution for a particular site. So with that, I will hand it over to Mike from Ramble, who will get us started.
Thanks, Sue. So my presentation, I'm going to describe and compare 4G versus 5G systems, and talk a little bit about the interplay between the system type and the CLCPA goals of deep decarbonization and renewable energy on the grid. Here's a brief graphic describing the evolution of thermal energy networks. As Sue mentioned, the early generations were heating only. First through third, fourth generation could be heating only, or could also have cooling if you install 2 more pipes in a cooling district, if that makes sense. And fifth generation, also called ambient loop, is even lower temperature. So you can see that the temperature has decreased through the generations. And with fourth and fifth generation, the temperatures are low enough that now we can use heat pumps, and that's a way to efficiently decarbonize the heating space. Here's some typical characteristics of fourth and fifth generation thermal energy networks. Primary concept I covered in the previous slide. So the number of pipes, if it's heating only, 4G, they would have 2 pipes, otherwise would have 4 for the cooling as well. They're often insulated steel or insulated high temperature polymer sometimes now for heating, and insulated polymer for cooling. 5G systems come in 1 or 2 pipe varieties, and they typically have uninsulated polymer pipes. I put some temperature ranges down here. These are not set in stone. It's just trying to be indicative. There's certainly some that are outside of those ranges as well. Note the delta T is the difference between the supply temperature and the return temperature, and the larger that is, the more thermal energy can be carried in a given pipe. And for 4G systems, they do have a larger delta T, which can accommodate, so use smaller pipe diameters as compared to 5G system, lower delta T. The next 2 slides will talk about performance aspects differences between 4 and 5G. The energy exchange is different between the two. 4G is really just a one-way energy transfer from the central plant to the customers. You can leverage effects of simultaneous cooling. If you have a central cooling network, then you can have heat recovery chillers in the central plant. But otherwise, there's not direct interaction like a 5G system can have, direct sharing of thermal energy between customers as well as with central sources. The thermal sources that can be used are the same in terms of geothermal or air source or wastewater. Things like that are all viable sources for either system and the heat pumps that are associated with them. Now note that the 5G, since it's a thermal source network with an ambient temperature, can accommodate the addition of thermal sources anywhere along the loop. With 4G, you need to bring that low temperature, low grade heat to the central plant first. But with high temperature, if you do have high temperature waste heat available, then 4G can use that more efficiently than 5G. Either one can use it, but 4G can use it potentially directly. Thermal losses, so 4G thermal losses are much lower than in previous generations with high temperatures, but they're not zero, and they are considered negligible for 5G systems. Central plant in a 4G system facilitates some features that give it some demand flexibility, redundancy, and resilience. So since the centralized system, centralized equipment, you can easily accommodate thermal energy storage. It could be chilled water or hot water or both. Also, it's easy to install redundant equipment and backup sources, which could include non-electric sources for resiliency or potentially for demand flexibility. When I say demand flexibility, that's the ability to reduce electrical demand for the grid. And the central plant, it's easy to dispatch electrical demand flexibility because of the thermal energy storage and the non-electric sources as backup or peaking. It's also easy to plug and play new technologies in one place if you have a central plant versus at every building like for a 5G. 5G systems, they do have more thermal inertia, say, than an individual system, individual building heat pump solution, and that does reduce the peak, but it's not really dispatchable unless you have thermal energy storage or non-electric alternate assets. So the capital cost, I would say to start with, you need to analyze it for each case-by-case basis, but here's some generalities. So ammunition for questions later, I think. This energy center and all the equipment that goes in it and the distribution system itself for a 4G system is more expensive generally than for a 5G system, with less equipment, centralized equipment, and lower cost piping materials. The building modifications can vary greatly in either case, the level of cost for building modifications. So for either case, there's typically a building heat exchanger to hydraulically separate the loop from the buildings. But in a 4G system, if your building systems can accommodate, they're hydronic already using water and can accommodate the temperatures provided by the system, then there can be minimal expenses in retrofit, but that's not always the case. And for 5G systems, they will always require heat pumps in the buildings and the space, to accommodate those heat pumps. They also potentially could require electrical capacity upgrades for those heat pumps, and then they still need to interface to the existing HVAC system, just like the 4G would. What else? So capital costs. There's certain features of a 4G that can help reduce capital costs. You can reduce the total capacity requirement because you have load diversity. Let me move on. I got 3 minutes left. The operational cost, due to demand flexibility, can be a benefit for 4G because you can use electricity when it's cheaper. Quick note on grid evolution. So the CLCPA calls for 70% renewables on the grid by 2030, 100% zero carbon by 2040. We are behind schedule, but still planning to be at 52% by 2030. And we know that intermittent renewables are going to make it difficult to manage the grid. So looking at the Danish example, in 2015, they were essentially where we are now at 55%, now in 2030, where we plan to be. And the demand, the blue line at the top, didn't exceed the renewable output, but fast forward to 2023, and now they're at about 87% renewables. Hourly data show the renewables regularly outpace the demand. And without thermal energy storage, then they would need to curtail that so that they use their largest demand flexibility lever in the Danish grid is thermal energy storage. And it's 1% is the cost of battery storage. Final point is looking at adopting TENS at scale and how that might affect the grid. Business as usual, we use fossil fuel for heating, electricity for other uses. If we go to individual heat pumps solution, we will need heat pumps in the buildings and the electrical capacity to accommodate that, which will be upgrades throughout the system. And so this represents kind of the maximum impact to the grid, especially if you used air source heat pumps. With a 5G system, we will have heat pumps in the building still, potentially requiring electrical upgrades, potentially not as much as for the individual building case because of more efficient heat pumps on a 5G system and the thermal inertia. 4G approach would require no heat pumps in the buildings. You definitely need electricity to the central energy plant, but thermal energy storage and non-electric peaking and backup options can limit that. So this represents kind of the lowest impact to the grid of the three options. So in conclusion, there's no one-size-fits-all solution. 4G, 5G, and individual heat pumps all have their applications. There are also hybrid 4G, 5G solutions that are possible. Use holistic planning to get your best result. so you know what you're getting. And we should be designing for systems that work today while still considering how the future grid and the 10 implementation affect each other. Thank you.
All right, me again. Brian Urlaub, Salas O'Brien. I get to have a little more fun now because that last presentation was boring in my mind. I like to tell stories, and stories are best told when you actually have projects you can talk about, and that gets to be a lot more fun. And I think we learn more from actually doing things versus just visualizing them. So we're going to talk a little bit about a few different projects and a couple different, as Mike was alluding to, a couple different ways you can do these types of systems between 4G and 5G. We've done both on many occasions, and this first example here is Ball State University. And I don't know how many of you know Ball State that converted their campus, so most of you. Yeah, this was the first higher ed university that actually got off of steam, which was still firing coal for their steam plant, and fully converted to an electrified geothermal system for their entire campus, which was pretty impressive. And it was about a decade-long project, which, obviously proved to be rather difficult. The drilling on that site was extremely difficult. I hate to say this, but I believe 3 drilling companies went out of business because of that project that didn't bid it correctly due to the geology and what they were trying to do. And there was a huge learning curve. So we learned a lot there. But anyway, this is a 4G system. And let's see if I have a little bit about the project here. There's 2 central energy plants that have York CYK centrifugal chillers. And one thing I just want to point out and get clear real quick with this audience, I hear a lot about simultaneous heating and cooling, and I hear that being used incorrectly. With the 5G system, when you have multiple buildings and heat pumps, that is not simultaneous heating and cooling. That's load sharing or energy sharing, thermal energy sharing. Simultaneous traditionally is meant by one device, one lift doing 2 jobs, meaning a chiller that's providing hot water and cold water at the exact same moment. That's simultaneous heating and cooling. That's only done with a central plant. Now, you could have a 5G with central plants in each building providing simultaneous for the building, but to load share or have simultaneous on a network, if it's not a central plant, that's not possible. You're going to have one compressor doing cooling, one compressor doing heating. That's not simultaneous. That's just sharing energy back and forth because you're still doing 2 lifts, 2 jobs. So just want to clear that up, make sure everybody understands that. This particular 4G system here, simultaneous heating and cooling. So that's where you gain the most efficiency in these type systems. With 4G, the best efficiency gain is when you can take all that simultaneous load and do it with one lift, and your COPs are now 8 to 10 to do that work because you're doing 2 things with one lift, okay? That's where that big efficiency gain comes in. And as Mike mentioned, getting to the lower temperatures is huge because now we can use heat pumps. If we're gonna be above 180 or above, heat pumps are really very difficult to utilize without cascading and dramatically decreasing your efficiency by putting them in series. So this is a very interesting project. This is a hot water, chilled water network. The reason why they stuck with this particular type system was because that's what they had. They had a chilled water network. So instead of abandoning that and going to a 5G system, they already had infrastructure there. So when you already have infrastructure, like a lot of urban areas do with steam networks and chilled water networks, it's hard to kind of just abandon all that and go to a 5G. Doesn't make a ton of sense that way, okay? But so this is a 4-pipe system, and then of course there's 2 massive geothermal bore fields for each plant that feed the energy for those plants at this particular site. So that's what we call a 4G. That's really how that operates. Now they don't have to be to that scale. You can actually still have multiple energy sources. You could have distributed thermal assets. You could have thermal storage, a lot of different technologies, and that is one benefit of 4G but it all has to come to a central location. Okay, and that's the challenge when you start getting into neighborhoods and looking at communities. You probably don't have an area for one large asset to feed a central plant. You got to have smaller assets that can feed in multiple locations, which lends us to the 5G approach. Okay, so That was Ball State. This is one of the energy plants. You can see the York chillers up there. They were pretty large. That was one thing we learned on that project is you really got to watch your turn down with large central plants. They don't have enough turn down on those chillers. So they run into a few issues at very low load scenarios. So now we're getting into more of the 5G. Now there's a couple different ways we can do 5G, right? It doesn't have to be what we call a single pipe all the time. Now I traditionally like single pipe just because my first inclination is to go to cost. With all these systems, we've got to keep cost in mind. We've got to reduce cost. What costs more, 2 pipes or 1 pipe? Right, pretty simple. Don't have to get out the calculator for that. 1 pipe is cheaper, all right? But not only that, there's other inherent things that go along with the 1 pipe that you can really help reduce costs and parasitic pumping energy, et cetera, if it's done a certain way. Now, this is a neat project in West Union, Iowa that's actually been around for like 10 years, over 10 years. This was actually built through the USDA grant. Back then, they were redoing their downtown streets and all their sewers and roadways and storm, et cetera, and they got this grant to install a thermal energy network. They didn't even know what it was called back then. And so they put this in. There's 56 buildings, I believe, tied to this system. You can see here. They didn't build it out all at first. They put in all the piping in the streets. It's a 2-pipe ambient system. They put in 1 bore field, and they had 14 users actually connect to the system the first go around. And then it's been that way ever since. They have not had any more users, even though the pipes are sticking in their buildings since then. And the primary reason is because they also have gas there and they have to pay out of their own pockets to retrofit their own building to connect to it. So we got involved because they were actually going to decommission this thing, turn it off and go back to gas and tell 14 buildings to go back to gas. And we're like, whoa, hold on. You have an amazing system here. Don't get ahead of yourself. So we went back in, we helped them get a better maintenance on O&M contract to really bring this thing back to life because they were, I hate to say this, but they were getting gouged by the person that was doing the maintenance. And so then they ended up getting a 3-year contract, so the maintenance cost came way down. So now the user group reserves were being able to, build over time and not be depleted because there wasn't a lot of maintenance. They literally turned the computer on, watched it run, and drove 3 hours back to their office. And they were getting paid for all of that. Anyway, then we also analyzed how much capacity is still available for more buildings without adding the additional bore field. Now the other bore field connections are ready to go. The vault is there, everything's there. You just got to drill and put the bores in. But they haven't spent the money to do that because they haven't had more users join. And so after our analysis, we went through and found that you could add about 4 or 5 more buildings before they start to run into capacity problems, and then they would need to add another bore field. Still need to help find, some capital for those folks to be able to do that. But this is a really interesting system, but it's a 2-pipe ambient. Everybody gets the same temperature basically throughout the network. And that's the benefit to a 2-pipe, is that everybody gets the same temperature, which means everybody's identically the same from an efficiency perspective, which is a little different with the single pipe, okay? So now let's go to a single pipe. This was the first one that I was ever involved with it's been 7 years now. It's been in operation for 2 years. 312 homes, or single family, and there's a couple townhomes and row houses that are involved, but basically mostly single family outside of Toronto. And there's 2 miles of 6-inch pipe. So we have about a 450 to 500 ton load here with a 6-inch pipe. And we're running less than 500 GPM through this system on the ambient pipe. If this was a 2-pipe, you'd have to double that flow in order to get everybody the same energy. And if the energy source was in one location. Well, as you can see here, there isn't one location to put a big energy source for 312 homes. Everything is located in the street. We had to distribute those resources out because there wasn't a big field. There wasn't a parking lot. So now, of course, this is a greenfield site. This was brand new. But it kind of lends itself, I think Jamie mentioned this morning at the keynote, new construction, this should be the standard for new construction. Why even put gas in here? Just go right to this. And you put it all right in the street as you build out the development. But anyway, so the key to a single pipe is having those distributed resources and injecting in multiple places. Otherwise, you don't save pump energy. You don't save your flow rate and your pipe size, and all that cost goes up because you're putting all the energy in one location. And I've seen this from other designs where they've got one spot to put energy in. Well, then a single pipe probably doesn't make a lot of sense, because now you got to over pump comparative to a two pipe. The idea of the single pipe is distributed energy to distributed buildings. And then you just manage the temperature between each resource. That way you can really slow the flow down. So for instance, and the resource matters. Like, what's the temperature of the resource? What if it's a sewage heat recovery versus GEO in multiple locations, and adding that in, keeping your temperatures higher? The warmer or the more consistent you can keep the temperature to between 50 and 60, the lower, oh, I gotta stop. The lower you can slow the flow down. So, there's a lot to these, but really interesting stuff. This was all, like I said, built in the street. This was another great project I know, Rachel, you were involved with, but I gotta stop here. So anyway, with that, I think we all know this project, right? Framingham. So, all right, thank you. I went up, too many stories. You should have been like waiting in there next time. I like that more than software.
Good afternoon. I'm Steve Gerges. I'm with Wendell. I'm part of their energy practice. I'm a senior project development manager. I know that's engineer. I know that's a mouthful. Wendell is here for this is our first conference. We're thrilled to be here. So far, we had a big day. We won the top job for the firehouse at Ithaca. And I want to keep the mood going. Today I'm going to talk to you about steam to low temperature hot water conversions, which is, I think, a pretty key component to the thermal energy networks that both Brian and Mike spoke about. So what am I going to cover today? We're going to go through key considerations, financial strategies, the challenges that you encounter along the way of converting these buildings. And we're going to walk you through a couple of case studies that we picked out, good examples of projects where we've done that. They're in final design and about to go to construction. So this is how I like viewing thermal energy networks, sort of a bridge being built from both sides. A lot of things happening at both ends of the bridge. However, for both sides to meet at that point in space and time in the near, not too distant future, the building side of things has to well, you have to have the demand for it, right? The heating and cooling demands. But at the same time, those heating and cooling demands have to be compatible with the requirements of the network. And they also have to be done in a cost-effective manner to the client. So how do we do that? Well, let's talk about some of the background first. Benefits of converting to low temperature hot water. You obviously get energy efficiency improvements. Low temperature, you get less heat loss for the run of pipe in the building. And in the case of steam, since it is a closed loop system, you're not witnessing the energy loss through dumping condensate or having failed traps and venting steam. You also have operational cost reductions. There's less maintenance associated with these systems. They're less extreme as compared to low temperature hot water. I mean, as compared to steam or to medium temp or high temp hot water. You get less pipe failures, less trap failures, and so on. And then the way to kind of spin it to the client is that it's one manner into, by doing the conversion, excuse me, by doing the conversion, you're actually you're replacing aging infrastructure, and that's, again, it gives you that opportunity to do that and also to improve control over the system. So key considerations, you obviously have to look at what you have, what you can reuse, and you have to understand the capacities of the systems and types of systems that are in place. Do you have cooling at the facility? Are you going to keep your chillers, whether as a primary source of cooling, backup, so on and so forth? You have to look at temperature requirements. I know that the conversation here is mostly geared towards steam conversion, but many of the buildings that we encounter are kind of a mix of both. You have steam coming into the building or steam generated at the central boiler plant gets distributed, and then it gets converted to, medium temp or 180-degree water to go to radiators or, reheat coils, and then the steam goes to the preheats and is used for other process purposes. So you have to kind of assess the compatibility of the existing system, what you can reuse, and then the components that you are going to reuse, such as like the low temperature or the hot water coils, you may have to stress test them to see if they can handle the lower temperatures, and you typically do that by, picking the coldest day and kind of dialing down the temperature and kind of playing like limbo and seeing how low you can go, or and then finding out that you may not have to replace all of those coils, but just in select locations. And in some instances, you might have to beef up your building envelope. That might be a cheaper alternative than to replace mechanical coils or equipment. The other thing that you want to consider is that this isn't something that you do in one fell swoop. You typically want to do it in a phased approach, keeping in mind the time or, the time when the network will arrive at your location so that you can connect to it. A big thing that you have to think about is how you're going to justify the cost of this. These upgrades or conversions are not cheap, and you will not get a simple payback on these things. So we typically look at these conversions in terms of life cycle, looking at the life of the equipment or another predefined lifetime. Maybe the client has some certain requirements, and you take into account all the costs associated and the benefits over the life of that equipment and the life of that conversion, and you would compare that to the do-nothing case or the business as usual case, which doesn't cost nothing. Another thing that we like to do is we like to leverage incentives. Some of the ones that Sue mentioned, things like the IRA if possible, and other rebates and grants that might be available. And then sometimes the stakeholders themselves, the clients, have to come up with the money, or they have money set aside and kind of perform internal grants. And then the other thing like the last point, which is operational savings and reinvestment, we typically look at ways to maybe even package these conversions with other ECMs so that you can actually get a payback, and maybe not get a payback, but use some of the savings from the other measures to buy down that project over the course of the lifetime of the equipment. So again, the challenges are technical challenges, figuring out what you have and how to convert it in a very cost-effective way. That kind of leads into the financials. And then the other challenge is usually talking to a client and managing their expectations as to how much this is going to cost, because a lot of clients, and this has happened to everyone I'm sure, they have an idea like, oh, this is going to pay for itself because it's an energy project, or this is going to pay for itself because it's a decarbonization. And you really have to be careful and define that for them, what the expectations are. So the case studies. First one is a private university. We cannot disclose the name for confidentiality reasons. It was a project for a laboratory electrification. It involved pretty much the building itself. Let me show you like the initial setup. It was connected to a district steam system, district cooling system, and what they wanted to do was to electrify the whole building, get it off of the steam plant. And the challenges that were there were obviously, reusing the coils, the hot water coils, and getting them to function with the lower temperature hot water, we went with 140. And then getting rid of some of the steam uses in the building, like the preheat coils, the humidification for the labs, and some of the other process uses, such as glassware washers, autoclaves, and the like. After the conversion, this is what it kind of looked like. We went ahead with a 210-ton heat pump. It's going to serve all the hot water needs for the building, and most of the chilled water. We still have to supplement off the district chilled water loop. This particular building is part of a community cluster, meaning that the bore field is going to be shared by 3 or 4 buildings. So this is the first phase of that, and they only built out a partial portion of the bore field. 3 minutes. I'm almost done. So as it stands, they're going to probably handle 90% of the load of the building with this heat pump. And then once the rest of the field is built out and the other buildings are connected, they'll be fully transitioned to heat pump, and all the buildings will be electrified. The last one is an interesting building. It's not part of a district or a community system, but it's an interesting building nonetheless. It's the Brooklyn Museum. Huge building, 540,000 square feet. They wanted to decarbonize this building. They had a goal to decrease the carbon emissions by 50%. It was part of an initiative that DCAS had, and kind of, I guess, planning ahead for the local law 97, the effects from local law 97 down in New York City. So the centerpiece of this, well, the existing system was essentially, the heating system was 3, I think they were like 8 million BTU per hour boilers that served, again, mixed use. The steam went to heat exchangers. Those were converted to hot water, but there were also other steam coils in the building that used steam, and they wanted to convert that all to low temp hot water. We kind of monitored the building from the BMS and quickly determined that there was an opportunity here for simultaneous heating and cooling. And that was kind of the centerpiece of our conversion. We kind of took advantage of that high COP from the heat recovery, and were able to essentially handle about 35% of the building loads in terms of heating and cooling. And then we kind of packaged that with a bunch of other ECMs or EEMs, energy efficiency measures, to sort of make it like to kind of enhance the life cycle cost. In the end, we saved almost 3,200 metric tons of CO2, or we predict we're going to save that, and 444,000 therms of gas. And I think what we're also applying for are the incentives through Con Ed. This is a NYPA customer, so the electricity is bought from NYPA but delivered by Con Ed, so they're not eligible for some of the grants and funds that Sue described through NYSERDA. This is just a schematic of what the heat recovery chiller looks like, and the load profile that we pieced together from whole building energy simulation and some of the load data that we obtained from the metering. And that's it. I'm gonna get going. Thanks.
Thanks, Steve. I just want to make one comment about the funding availability for PON 5614, which is the large-scale thermal program I described at the beginning. Fortunately, we do have funding available that could support project sites throughout New York State, regardless of whether or not they're a NYPA customer. So we do have funding, whether or not a project pays SBC. So please don't be deterred by that. If you're a Muni customer or on Long Island, it would still be eligible for the 5614 program, and we would also be interested in determining if you would be a good fit for a feasibility study for large-scale thermal through FlexTech. So open it up to questions.
Hello, Seth Berkman with NYSERDA. Thanks everyone for your very informative presentations. Definitely learned a lot. This might be most for Mike and Brian, but anybody feel free. I was curious about project financing and how long these projects are expected to live or be operational, and how, when you're developing a project, you and the clients that you're working with think about sort of amortization periods and how long they have to recover the cost of these projects. Obviously, on a campus system, I'd imagine it's like different from the way that utilities think about capital financing. So if you could speak to that a little bit, I think would be informative. Thank you.
Joe? Yeah, you're right. First of all, campuses are 100% different than a utility model. Most of the campuses that we're with are private colleges, so they're using endowment funds and maybe other private financing that they can secure. That's usually pretty low rates to do capital projects, depending on where they're sitting financially. The interesting thing about paybacks or return on investments, in amortization and life cycle, it's interesting because a lot of people look at geothermal and they do a 30-year life cycle cost, but that it just was brought up earlier on a different session about what's the salvage value of a geothermal loop field, because it's there after 30 years. It still provides energy after 30 years. It doesn't run out of energy at your 30 or 50 or 80. So how do you properly assess the value of that at the end of the 30 years if that's their, rate schedule that they want to look at, right? So life cycle costing is challenging now because these assets are different. They're not a traditional asset where at year 30, you scrap it and put another one in. So that has to be looked at differently. And there's also a lot of social cost of carbon that's being brought into the private university cost metrics, which changes things dramatically when you start looking at the social cost of carbon. From a utility model, real quick, there's a bunch of utility folks here. They know better than I do, but amortization certainly is more, I think, what they would see as a traditional asset. So gas, electric, 60 years, 80 years, whatever that might be. And then, their financing mechanisms are different because, if they're a regulated utility, they're public entities, so bonds and but usually very good discount rates. So, but their paybacks aren't measured the same way. It's totally different kind of outlook on how that works. That answered that.
Tony Gelber from Pratt. Hey guys and woman. You totally confused me on the 4G, 5G thing. Can you try to explain it? So one pipe, two pipes, and 80. Come on, guys. Clear this up.
Sue only gave me 12 minutes, sorry.
That's a good
It is confusing. So the 4G system at its heart has a central plant that distributes final finished temperature water to all the buildings. Whereas a 5G system has the heat pumps in each individual building, and you circulate ambient temperature water as the thermal source for those heat pumps.
So let's say we have an ambient one pipe loop around the campus with heat pumps in each building. That's a 5G.
Yes. Yeah.
If we have a two pipe with one temperature with heat pumps in the building, that's still 5G? That's still.
Yeah, sounds like ambient loop 5G.
Okay. If we have a hot loop and a cold loop going around, that's 4G.
Well, generally, yes. If it's finished water, if you don't need heat pumps in the buildings, then it's 4G.
You don't need. All right, I'll see you later.
A two-pipe ambient loop, one pipe will be warmer than the other, but it's not final temperature.
I just want to say we didn't come up with these terms either. That's a whole other, yeah.
Max Shavago with NY-GEO. Brian, on the almost 3,000 borehole system, how far apart were those boreholes?
Well, that was a long time ago. So that was back when, the 20-foot rule wasn't and those were shallower. So a lot of those are 15-foot on center. But I wanted to come back to that. I'm glad you asked that question, because the reason why those drillers had such a hard time, out of all those boreholes, you know how many test bores they did on that site? One. They should have done probably 10 maybe across that site, especially after the first one was pretty difficult, to really get a better feel for drilling conditions. That would have helped those drillers tremendously and the cost of the project.
And you're seeing that all those boreholes are working effectively, I'm assuming.
Yeah, they haven't had really any heat buildup. There's actually a lot of water flow on that site, below grade, hydraulic water flow. So yeah, they haven't had any net effects long-term of heat buildup. So the spacing wasn't necessarily critical there. But it could be, depending on the load profile and the geology.
Am I missing somebody? Okay.
So in the Brooklyn project, you showed the steam conversion. That was, I think, there you go. So we have like 1 million square feet of steam. So when we look at converting that to something else, the costs are, I don't know, we're figuring like $150 a square foot between converting all the piping, all the radiation. It's cost prohibitive. So what did you find in your Brooklyn project? What did you have a number per square foot for cost?
For that upgrade, I can get you that number. I don't have that number offhand, but what we were trying to do when we were converting was and the way it's just the way the building was laid out. The mechanical rooms had the steam preheat coils all in one location, so it was pretty straightforward to do. All we had to do was run risers up to the mechanical rooms. The other terminal devices were, for the most part, hot water. So it's not going to be the $150 per square foot that you're seeing. I mean, there just are some buildings where they're all steam and there's nothing you can do. You have to rerun new piping, and you definitely don't want to reuse the steam piping. That's
right. So I saw in your when you have air handlers and you could just change the coil in the air handler.
Yeah.
That looks like much more a reasonable project.
Well, we had to change some of the coils in the air handling units on the hot water side because they wouldn't make the discharge temperatures that,
Okay.
For the flows and the air conditioning, whatever. But the steam coils, we had to change the coils and the piping. But as I said, those were confined to mechanical rooms, so it kind of lended itself to that. And at the same time, we had the heat recovery chiller that, as Brian said, could do everything in one lift and get a high COP, so that kind of contributed more to the positive cash flow of the project.
Okay, thank you very much.
Sure.
Anyone else?
Quiet group, everybody's looking for beer, I think. They're ready.
Hey, you guys know me. Ryan LaValle with Ramble. Steve, this is for you. The Brooklyn project. I noticed you showed the simultaneous, or the opportunity for the simultaneous heating and cooling. So you showed the heating loads and the cooling loads.
Right.
I think you had the timeline. It was like late fall and winter, like that you showed for that specific time period, and you showed quite high cooling loads for the Brooklyn project. What were those cooling loads? Because traditionally, during that timeline for like a typical building, you don't see cooling loads that high. You guys were able to take advantage of that with the heat recovery chiller.
I think some of those were dehumidification loads. Like they had to maintain humidity in certain spaces. Like sort of a set point, like I think it was like 50% or something like that for the artwork and the masterpieces.
Okay, because it was the museum. Yes,
but yeah, I like I said, I wasn't really involved in the building modeling portion of that, but I suspect that's what it is. Yeah. Thank you.
I think that might be it.
All right. Thanks, everyone. Enjoy happy hour.